Can you start the? Okay, so let's get started. So today we are going to continue from where we left off and talk about communication and distributed systems. Like last time, we are going to have three parts to the lecture. First, I'm going to give you an overview of some principles behind the communication techniques in distributed systems. Then we'll start talking about one particular approach for building distributed applications and enabling communication, which is remote procedure calls or RPCs. And we'll talk about how RPCs work. And then in the last part, we'll talk a little bit about the implementation details of RPCs. Okay. And I've also listed what is coming next for the class. So next time we'll continue that discussion and talk about RMIs, which is how RPCs work in an object-oriented fashion, specifically how Java has these concepts embedded in it. We'll also talk a little bit about stream communication. Okay, but that's for next time. Today, let's start with messages and message-oriented communication. So I think the high-level picture you need to keep in mind is whenever you want communication to be enabled between two or more processes in the system, okay, there are two ways to do it. There's the unstructured approach and there's a structured approach. Okay? So let's understand a little bit about each of these. Okay, and by and large, we are going to focus mostly on the structured approach. Okay? But it's important for you to understand unstructured methods of communication. Okay, so let's assume you have two processes. Okay, initially, you don't need to even assume that they are processes on two different machines. They could be processes on your own machine, a single machine. Okay, how can they communicate with each other? Okay. One approach, which is called unstructured, is that you use some sort of a shared memory or a shared buffer for communication. Okay. Process A is going to put some data in that shared buffer. Okay. And process B also has access to that same shared buffer. It can go and take that data from that buffer and do something with it. Okay. So you're essentially using a shared buffer to communicate. Okay. So you have processes A and B. Okay, and here is your shared buffer. Okay, so you can essentially access that shared buffer and communicate. Okay, this is called unstructured because the buffer has no structure associated with just a piece of memory. Okay, you can put whatever data you want, and then the other process has to interpret that data and do something with it. Okay, that's one approach. Okay, now in structured communication, you are going to essentially communicate by exchanging messages. Rather than using a shared piece of memory, you're going to explicitly send a message. A is going to send a message to B. B can receive that message and process it. And B can then send another message to A, which could be the response to the first message, and so on and so forth. Okay? So you're using what is called explicit message passing or inter-process communication for this to occur. Okay? And this will refer to as structured communication because we are going to use explicit messages rather than implicit use of buffers to send data back and forth. Okay? Now, there are multiple ways to have message passing implemented in your system. One is to use what is called sockets, which we are going to talk about. And then the other is called using remote procedure calls, which is also what we are going to talk about. Okay? Now, the important thing to keep in mind is that if these processes that are communicating are in a distributed system, they may be on different machines. Okay, so whatever I talked about actually has to occur over a network. Okay, because you could just have two processes on the same machine and they can communicate using messages or buffers, but so can they be on two different machines. Okay. Now, the thing you want to keep in mind is if you're using unstructured communication and your processes are on different machines, there has to be a way for you to share the buffer across machines. You want to make the memory accessible across machines. That ends up being a little more challenging than if you just had a shared memory on a single machine. Okay? But as I said, we are really not going to talk about unstructured communication or shared memory right now. Later on in the course, when we come to Spark, we'll see how it can use shared memory to enable communication. Okay, but for now, we are going to only focus on structured communication. Okay, is there any question here? Yes. So I think what the question is, what does it mean to say both need low-level communication support? I meant both structured and unstructured. Okay, so basically you have your application spread across a network. So you need communication infrastructure. Okay, so this is just a recap of what you should by and large know. This is a picture of a network protocol stack. Okay, and the picture you want to keep in mind is TCP/IP, because that is essentially the protocol stack that is used over the internet. All of the applications that we are going to be talking about in this class essentially assume that there is TCP/IP network support provided to you, and that's what is going to be used for enabling communication, whether it's structured or unstructured. Okay, and just so that you understand, protocol stacks also used a layer design, like we talked about last time. Okay, we talked about the layer design for designing applications. You have the same concept that originated in protocol stack. So you see there is a set of layers. There's a physical layer, data link layer, network layer, transport session, presentation, and application layer. Okay, each layer has a certain function associated with it. The physical layer is essentially either your wire that connects the machines, or it could be essentially a wireless channel like you use in Wi-Fi or cellular that is enabling communication at the lowest layer. Data link layer is something like a MAC layer or Ethernet that you have. Okay, network layer, in this case, our case is going to be IP. Okay, it enables hop-by-hop communication. Okay, transport layer is going to be TCP. Okay, TCP/IP essentially has TCP, which is a transport layer, and IP, which is a network layer. Okay, transport layers enable end-to-end communication, and network layer enables hop-by-hop communication, is responsible for routing. Okay, and then in the TCP/IP case, typically the session and the presentation layer is not necessarily present. That functionality is rolled up to the application layer. So if you need to do anything that involves sessions and whatnot, you essentially have to do that at an application layer. Okay. Now, when messages are sent, so let's assume there's a sender and a receiver at the two end. This is your network. The sender is at the application on machine 1. The receiver is at the application layer at machine 2. Okay, it's going to create a message. Okay, it's going to send it down the protocol stack or through TCP/IP protocol stack. The message percolates down the stack. It's going to go over a network. Okay, there may be multiple hops along the way, because you may have routers that forward your message, but eventually it gets to the destination and it goes up the protocol stack, is handed to the application. Okay, that's how message passing is going to work. Okay, this is basically a structure of a message once it actually is sent out on a network. Okay, the message part is what the application actually wrote. Okay, that's the message it wants to send. But as it goes down the protocol stack, each layer is going to add a header to it. Okay, so you will see here, there's an application layer header. This is an HTTP message. There's going to be an HTTP header. Okay, that tells the HTTP endpoint at the other side what to do with the message. Okay, and then you will have a TCP header, you will have an IP header, you may have an Ethernet header, and so on and so forth. Okay, and then when the message arrives at the other end, each layer looks at its specific header, okay, which will be whatever is that layer, decide what to do with the message, strip that header, and hand it back. Okay, so when the application receives it, it will only have the application layer header and the message. Is that clear? Okay, so this is something you should be generally familiar with, but I just mention it just in case. Okay. Now, in this course, later on, we are going to essentially have a middleware layer sitting between the transport layer and the application that's going to provide additional functionality to us. Okay, so let's think of this as a software layer above which the application runs, and that software layer provides other important protocol services. Okay, we'll give you here as an example on this slide: distributed commit, distributed transactions. There can be all kinds of services you can provide at the middleware layer. Okay, so that's something we will keep in mind. But for today, we will not assume any middleware. We'll just assume you have a TCP/IP stack, and you want to build a distributed application that has to communicate, okay, over a network. How are we going to do it? Okay, that's really what we want to understand. Okay. So the first and the simplest and the lowest level approach to write an application where two components communicate is to use what is called the socket interface. Okay, this is basically using TCP/IP to send messages. Okay, this is essentially the lowest layer of communication that you can have in a program. Okay, so socket is an abstraction that you are going to create. In the socket, you can read and write to the socket, and then the socket abstraction essentially uses TCP/IP to send messages. Okay, so essentially this socket is an abstraction that directly uses the protocol stack to send and receive messages. And there are several calls listed here, okay, which are what you are going to use to create socket and communicate. I'm going to show you in a picture how all of these work together. Okay, so we'll see how to write a very simple client and a server using a native socket interface. Okay, and that is what is shown in this picture. Okay, so essentially the client program is running on one machine, the server program is running on a different machine. Okay, they are connected over a network. Okay, it could be a local area network, it could be the internet, doesn't matter for this discussion, but they are essentially separated by a network. Okay, in the code of the client and the code of the server, you have to essentially call the socket interface that creates a network endpoint. Okay, the socket essentially creates a network address for communication. Okay, a network address is two components. Okay, it will have the IP address of the machine. Okay, that's something that's already going to be decided based on what machine the program is running on or the process is running on, and it's going to have a port number which is an endpoint. Okay, each program has to listen at a unique port. That's it. That is its network address on that machine. Okay, all packets arriving to it will have that address. It will have an IP address and a port number. Okay, so when you create a socket, you create open a new port. Okay, that gives you an address to listen or send messages. Okay, every program that runs on a machine has to have a unique port. Okay, many services that you already have on your machine have well-known port numbers. Okay, they listen at well-known addresses so that other clients know where to connect to. Okay, for example, HTTP has a port number 80. Okay, that's the unique port that you have for all HTTP by default. That's the default port number. You can change it, of course. But by default, when you start an HTTP service, it will listen on port 80. So if a browser needs to connect to a web server on a machine, it doesn't need to know what address to look for because there is a well-defined address. You just connect to that port number. Okay? But be that as it may, the server has to still create a socket and then connect to that port, and so does the client. Okay, so server creates a socket, it binds to a port number, it then starts listening on that port number, and then it says accept, and the accept call will then start accepting connections, okay, all the network messages that come. Okay. And then once you have accepted a connection, then you will sit in a while loop, reading and writing messages from whoever has connected to that server. Okay, yes, question. Can you repeat the question? What's the question?
Would be considered as unstructured communication message?
Okay, so question is, are message queues considered unstructured communication? That's your question, right? That's the question. Okay, so we'll come to this concept of message queuing later. Message queuing is a message passing interface. It is not unstructured. It is a message oriented communication. So it comes under structured communication. Okay, so but we'll get to message queues in a little bit, not today. Okay, so in any case, I think the server code has to have, you call the socket call, you make a bind to a port number, you listen, accept. Then once you've accepted, you can read or write to the client. Okay, and on the client side, you have to create a socket, and then you call connect to the server. Okay, this creates a TCP/IP connection between the client and the server. Okay, this establishes that connection. Okay, so this is why you have this arrow here saying synchronization point. The client actually has a opened by TCP/IP connection to the server, and then the client and server can communicate once this has happened. Okay, they can read and write, and then once you're done with whatever you do, you close the connection. Okay, this is how you are going to write a bare bones program that allows a process on one machine to communicate to a process on another machine. Okay, and I'll show you an example of whatever I have on the previous slide. This is Python code that exactly does what I showed you on the previous slide. Okay, the top part is the client code. Okay, you can see that it calls a socket interface, and then it just calls connect. Okay, that's what I said here. Okay, you call socket, then you connect, and then at this point you can read and write, but that's not shown in the snippet of code there. Okay, and here is your trivial server. You call socket, it kind of creates a new socket. You bind that socket. In this case, you're creating a trivial HTTP server. So you can bind it to port 80. Okay, that's where HTTP servers listen on. Okay, then you say listen on that port. Okay, and then you sit in a while loop saying accept new connections. If another client wants to connect, you accept a connection, and then you can do something. You can read and write to that client. Okay, and then you close the connection, which is not shown. Is that clear? Okay. So this is code you would have to write, okay, in order for the process to communicate with another process, the client to talk to a server. Is that clear? Okay. So this is socket level communication. Okay, a lot of code to write. Well, not lot, but some code to write. But you have to decide where is the server, what port number, what messages to send. All of this is something that you have to decide and write in your code. Okay, this is the networking part. This is not really any application level code. This is the networking part of your application. Okay, the application not even shown here. Okay, but this is what you have to do. Yes. Okay. For connect, can you use IP addresses? You can either use an IP address or you can use the name of the server, which will translate that to an IP address. So here it says just python.org, but you could have given a numeric IP address as well. Okay, yes, question. Okay, question is what's the difference between a web socket and a socket? A web socket is just an abstraction that is much higher level, that is at an HTTP level. When we talk about web, we will get to that. Web sockets are nothing to do with network socket. They're something at a higher level that operate at HTTP that give a slightly different abstraction. The usage of the term socket is confusing, but web sockets really are not really sockets like this. Okay? When we get to the web part of the lecture, you can ask that question and we will have known enough to answer that question. At this point, we haven't talked about HTTP to answer that question. Okay, but it is not really socket. Okay, these are socket. This is what actually allows you to do TCP/IP, use TCP/IP to communicate. Okay, okay. So now, but if you need to know more, there is a link here. You can go look at it. We'll also give you a sample code you can play with and try to see how it works and whatnot. Okay. Okay, now let's just take a peek underneath and then we will try to do RPCs and see how you can do something at a much higher level of abstraction. Okay, now when you try to set up a TCP/IP connection between a client and a server, it's instructive again to know what is actually happening under the hoods. Okay, so there's a little bit of networking than distributed system. It's just good to understand because when we go and talk about things like HTTP 2.0 and so on, I'll say this is why HTTP 2.0 was designed to remove all these overheads, and at that point you'll understand why I'm even talking about all this. Okay, so how does a TCP/IP connection get established? So the client and the server, okay, when the client creates a socket, the server creates a socket, and then they essentially try to connect to one another to establish this connection. These are the messages that are getting passed between the client and the server. The client is going to send what is called a SYN message. Okay? SYN message says, let's establish a connection. Is a message to the server. Okay? Let's establish this connection. The server sends back a SYN message saying, yes, let's establish a connection. And it sends an acknowledgement saying, I received your SYN. Acknowledgement just says that I received your message. So you send an ACK for that original SYN. Okay? That's message number 2 that's gone back. Okay? And then the client sends back an acknowledgement saying, yes, I got your SYN. Okay? So these 3 messages have to be exchanged in order for the connection to be even established. Okay? The client says, let's establish a connection. Server says, fine. Client says, yes, I got your message. Okay? So 3 messages have to go back and forth before anything can even happen. Okay? At this point, there is actually an active connection. Okay? This is where the socket at both ends have been connected with an active TCP/IP connection. And then you can send actual messages. Okay? In this case, you send a request message. So think of this as an HTTP request. You open a connection, your browser rather opens a connection, you send a HTTP request, you get back a response and you are done. That's all we want to do. Okay, client browser is wanting to send a request, get back a response. So once this is done, then you send a request. Okay? Request goes to the server, and that point client is done. It's done sending the request. You could of course send many messages. Okay? In this case, you're just sending one request message. Okay? But in general, you don't have to stop there. You can send multiple. But in this case, you do that, and then you say I'm done. So you send a fin message. Okay? Then you get an acknowledgement to the fin. Okay? And then you get a response to your request. And then you said I am done. The server says done sending the response. You get back an acknowledgement. Okay? So to send a single request message from the server to the client, so the client to the server, and to get back an answer, there is an overhead of 9 messages, of which the 2 messages are the ones that you actually care about. Okay, this extra 7 messages is all TCP/IP overhead to set up a connection, to tear down the connection. Okay, and by the way, this is called a 3-way handshake. Okay, TCP has this concept of a 3-way handshake. There's 3 messages have to go back and forth for you to establish a connection, and 3 more messages have to go back and forth for you to tear down the connection. Okay, so a lot of overhead just to send one request and one response. Okay, and later on, we are going to see how to reduce that overhead, because this does increase your network overhead for communication. Okay, for now, we'll just say that's what we have to do in order to get a TCP connection going. Yes, question. Okay, so question is, why are you acknowledging multiple messages? Right. So what TCP/IP does is it acknowledges the most recent message it has received in order. It doesn't send an acknowledgement for everything it has received. So you can batch. If you get message number 5, 6, 7, 8, you can say I got everything till 8. Okay? This is simply saying I got everything till the fin. So you got both the request and the fin. It's just because what you send is a acknowledgement with the sequence number. I say I got packet number 10. That's what you acknowledge. You don't say I got 9, 10. You don't send for each packet. Okay? That way you can batch the acknowledgement, reduce the overhead a little bit. Okay? So in this case, since 2 of these requests were received, in order, you can just say I got everything until fin. That's what it says. Okay. Okay. So there's a higher overhead that we have to pay. At this point, we are not going to worry about optimizing that overhead. Okay, but later on, when we talk about HTTP, you will see this has performance implication. Every time a browser makes a connection, it has to pay all of this price underneath. So there's a question of how are we going to optimize for it. That will come later. Okay, at this point, we are not trying to solve that problem, but something you should know. Okay, any questions on this? Okay, so we'll see now other ways for establishing communication. But before we get there, I want to talk about group communication, and we'll again look at ways to have group communication later on. This is just the concept. Okay? Group communication says you want one client or one machine to send a message to multiple machines. Okay? So you want to send a message to the group. Okay, how would you do it? There are 2 ways to do it. You send individual messages to everybody in the group, or you send one message with a group address and the network delivers it to everyone in the group. Okay? This is something like you want to send an email to a large number of recipients. You can just have all of their individual addresses in your mail, or you make a mailing list which has all of them and you just send to the mailing list which delivers it to everyone. Okay? Same concept. Okay? Because there are many cases where you want to actually communicate with a group of machines rather than sending n individual messages to each one in the group. You send one message and then you have a group address and not you don't have a list of addresses. You have a group address, and that group address is one where all the recipients are subscribed to. The network takes care of delivering it to all of those. Okay? This is called group communication. It's also called multicast in the networking terminology. Okay? There's also something called broadcast, which sends to everyone. Okay? But multicast just sends to a subset of entities that you want to communicate with. Okay? So there is lots of distributed applications where we will actually think about communicating with a group. Okay? And so you just need to know that there are interesting ways you can enable group communication. You can do this at the network layer. You can have application level libraries that do application level multicast and so on. Again, when we talk about these concepts, Later on, we'll think about how to do them. Okay, for now, you just need to know that there is also a way for you to communicate with the group. Okay, just as you set up a single socket, which enabled you to communicate with one other entity, you can essentially set up a socket with a group address and just do a send to that socket. The network will then deliver your packet to all of those or message to all of those entities. Okay, yes, question. Okay, question is this like the event bus? Okay, that we talked about. So you can think of it as event bus could use potentially multicast or group communication for events to be delivered to multiple recipients. Because the event bus itself is different from group communication, but one way you could implement it is if an event has to be delivered to multiple entities, you just send it to a group and then the network will send it to all of those entities. Okay, this is just how TCP/IP can be used to communicate with multiple machines with one message. Okay. All right. So we are done with part one. What we'll do now is switch to higher level abstraction and specifically remote procedure calls. Okay, are there any questions on what I've talked about so far? It's mostly networking background, but something you should know for what is coming next. Are there any questions on the? Okay. Yes, question. Okay, so question is, what about the issues which I really glossed over? Atomicity, message ordering, scalability. Again, when we talk about multicast in more detail, we'll get to that. But very quickly, what this is saying is atomicity says if I send a message to the group, either everybody in the group should receive it or nobody should receive it. Even if there are failures and some members actually crash by just sending it, the network guarantees that it's all or nothing property. That's called atomic sense. Message ordering sense, if I send two messages, they're delivered in order. And if I send I and then I send J, everybody gets I followed by J. It's not that some far off machine gets them in a different order. Okay, so that's called message ordering. Scalability simply means that you can scale to a very large number of groups. You can have tens of thousands of machines and you can send one message and it gets delivered efficiently. Okay? So these are all properties you want from group communication. But as I said, I'm not going to discuss a lot of how to do it here. Okay? This is just something you should keep in mind. And then, of course, starting at dynamic means static group just says once you create the group, its membership is fixed. Dynamic group says you can join or leave. It's like a mailing list. Okay, if you can just join a list at any time or leave, and then the list gets updated, that's a dynamic group. Static says you just set the number of recipients and it can't be changed. You have to delete the whole group in order and create a new one to change it. Okay, so these are all properties you want from group communication. Yes. Sorry, what's your question again? Oh, issues means these are all design consideration. Issue doesn't mean it's a disadvantage. Issue simply means if you want to design a group communication system, then these are all things you have to worry about in order to do it well. Okay, what is your group? What's your group characteristic? Are you going to provide atomicity? Are you going to provide ordering? Answer could be yes or no, right? And if it's yes, then how do you do it? All right. So now let's talk about remote procedure calls. So what I showed you in part one was low-level mechanisms by which you can create a distributed application and have them communicate. Okay? But that is requiring a programmer to essentially understand a lot of networking concepts. Right? So unless you know enough networking, you have to then write your own socket code, you have to communicate and do all of those extra things for you to write a distributed application. Okay? So the question we can ask is there a way to enable developers to write code, okay, without essentially also knowing a lot of networking concepts and yet make it a distributed application? Okay. So this will require that we provide a higher level of abstraction that programmers will program to, and yet you can write distributed application. You may not need to know a lot about TCP/IP. You may not need to know a lot about sockets, all the stuff I showed you. suppose you didn't know that. Okay? Can you write a distributed application and make it work well? Okay? The answer is, if you could provide higher level abstraction where some of these details are taken care of for you, you don't write the code, but the libraries take care of it for you, then you can program at a higher level of abstraction. There's still communication, but some of this is hidden from the application developer. Okay? So question is, how do you design abstractions that let you write distributed applications, okay, without having to deal with these low-level details? You could, of course, write applications using those low-level details and they'll work fine. But then, as I said, you need to write all of that code yourself. Okay? RPCs, or remote procedure calls, are one way to do this. Okay? Essentially, RPCs just let you write code as if you are writing a centralized program. Okay? So you don't actually deal with a lot of the networking concepts that I just showed you that involve socket. You just write code as if it is a normal program. Maybe if it's a Java program, you just write classes. Classes have methods and so on. Okay? And then when you invoke these methods, somehow they actually work as if they're a distributed application. Okay? So the goal is to provide abstractions that make, from a developer standpoint, distributed computing look like centralized computing. If you know how to program, you should be able to know how to write distributed programs. Okay? Is that possible? How will you do that? Okay? So this will make it much easier for lots of developers who just know how to write normal code to also write distributed application. Okay? That's one way to think about why we want RPCs. Okay? Another way to think about this is to see what we are going to do with message passing at a socket level. Okay? Suppose you want to write a socket level program. Okay? You basically have to think about what are the types of messages client has to send to a server. Okay? You might have a read message, you might have a write message, you might have all kinds of messages. You have to construct this message, send it. Okay? At the other end, you receive a message, you parse that message saying what is the client requesting. Maybe the client requests operation X, then you call some code to perform that X, then you send back a response. Okay? Then maybe the client asks for, sends another message with asking for something else. Then you again look at that message that's come over a socket saying, what does this client want? Say maybe it wants to do some other operation. You call some other code in your server, it performs that operation, you send back a reply, and so on. Okay? That is typically how you would write a socket program. Now, instead of sending a message and having the client parse it and call the right type of functions at the server to perform that operation, why can't the client directly call that function at the server? Okay, if you want to essentially call a method X, rather than sending a message which somehow indicates to the server saying invoke message X and then do something, why don't you just call that function directly? Okay? That will actually make it much easier to write this code. Okay, so that's essentially what a remote procedure call is. Okay? As the name remote procedure call suggests, you're essentially calling procedures or functions that are on remote machines. Okay? You're essentially invoking code that is not within your process, but resides on some other machine. Because by invoking a remote procedure, you can essentially perform distributed computations. And that is how you're going to write your application. Okay? So let me now explain this better with an example. Okay? Here is an example of a server process that essentially provides an add service. Okay? So the add service is going to take two arguments and sum it up and send back a response. Okay? So here is a client. Okay? Now, as far as RPCs is concerned, all that the client is going to do is call a function called add. In your code, you are just going to write add, and you're going to pass two arguments, ing. Okay? You're not going to say, let's set up a TCP IP connection, let's do a socket, let's do all of that code that I showed you. None of that is actually written by the program. Programmer simply calls add. Okay? It just so happens that add is not a function that's within this process. Normally, if you call a function, that for code for that function has to reside within this process. Okay? This is just a remote procedure. The code for add actually sits in a different process. It's in the server. Okay? Now, somehow when you call add, the runtime system is going to figure out this is not a local function. This is a remote procedure, a remote function. So what it is going to do for you is going to construct a message. Okay? Saying here's a procedure. Okay, the client wants to invoke add. Here are the two variables I and j that are arguments to add. Okay, and then this message is sent over the network. Okay. It arrives at the other end. Okay. The server is listening for requests. The server is going to say, here is a message. Okay, there's a request for add. Here are the arguments. So then you're going to actually invoke the implementation of add, perform the operation, and send back another message with the response. That's not shown in this picture, but a message goes back here, and the response comes here. And then when the add returns, it gets a response. That's the sum of the two variables. Okay. Now everything under the hoods is not written by the programmer. Programmer just wrote the code for add. Programmer just on this side just invoked add and just told the runtime system this is a remote procedure. Okay, and the runtime system has taken care of all this extra code that is going to construct a message, find the server, so set up a TCP/IP connection. All of that socket stuff is still there, but it's not written by the developer. Okay. Developer just writes code for remote functions and invokes this function. Okay. In the Java world, you are just going to write classes and you are going to say these are remote methods. These methods can be invoked over a network. Okay. And then the JVM is going to say, I can now listen for messages that invoke these methods over a network. I don't have to wait for other local objects to call these methods. Okay, so everything is then hidden from the programmer and then simplifies application development. There's a question, yes.
So how will the client know the server's port?
Okay. How will the client know the server's port? So I think there's a little bit of code you have to write at the beginning, but it's not like socket code. You are going to essentially say, I want to invoke this service. And there is something that figures out where's the IP address of the service and so on for you also. Okay. So that has to happen clearly. It's not magic. It's not that you just call add and somehow something figures out. But that code is not shown, but it's not like writing socket code. Okay. And we'll get to that as well when it show implementation. Yes, question. Yeah, the question is on the client side, do we need to consider how we are connecting to the server? As far as the developer is concerned, the answer is no. You are just actually invoking this add function. And you just specified that it's a remote function. Okay, so there is this entity called the stub. Okay, you'll see there's a stub on the client, there's a stub on the server. This is auto-generated code. Okay. When essentially there's an additional step when you write RPCs, there's something called an RPC compiler. It's going to take all your remote methods and it's going to generate code to construct messages and send it and all of that. That's called stub code. You don't write it, but you just say, these are my remote methods, these are my interfaces, that code is auto-generated. And then you basically link it to your program and all of this extra code becomes part of your process. Okay. So you only write your part of the code. The compiler, in this case, is called an RPC compiler, is going to do that for you. Okay. In JVM, it's basically the Java libraries and the JVM RMI libraries that take care of this for you. Okay. So as you can imagine, what has actually happened is we'll raise the level of abstraction for writing distributed application. Okay. We just think of our application as a sequence of methods. Okay. The methods now reside in different processes, because our application is distributed. Okay, so you say what goes in the server process, those methods or functions are written in the server process. What goes in the client goes in the client process. Okay, client functions can call functions on the server process, just as you call normal functions within your process. Okay? Or in the object-oriented world, just as you can call methods on objects, you can call methods on objects that reside on other machines. Okay, these are called remote methods. So you will just say object.foo, okay, just that object is actually sitting on some server machine. It's running in a process on some server machine. Okay, so it looks exactly the same. Okay, so you don't have to deal with all the networking details. Okay. This makes it much easier to write code as an application developer. Okay. And that was essentially the intent of designing these remote procedure calls. Any questions here? We're now going to get into details of how all of these happen, but is the concept clear? Okay. This question. Okay. What if there are two servers with the same method? So that's a good question. So there are, of course, ways to deal with all kinds of details that I glossed over here. So first thing is there could be many web servers, right? So you may say, which web server do I care? So you have to have some way to disambiguate. So there are multiple ways to deal with it. Each of these servers can register with a naming service saying, I provide this interface. Okay? And then the client can actually talk to this naming service and say, I need a service that provides this function. You may say, there is one that is here, one that's here. You can pick one. Okay, that's one way to do it. Or the client has to figure out which is its preferred version. Okay, and then you can basically pick that. So there are ways to deal with that. At this point, we won't worry about it. Okay? But so the simple way is that you just know where the server is running. Okay, you know, at least you say the server is running at this machine. That's the add method I want. Okay, so then that's simple. So you say, I want add method on machine B, you're done. Okay, so that's the simplest way. But the more complex way is you can actually go and look up a naming service. And that tells you all the services running on your network. Yes.
So does this actually wrap over the socket part and also the TCP part for us?
Okay, question is, does RPC is a wrapper over TCP IP and socket? So RPCs are built using sockets underneath, except that programmers don't write the socket code. The compiler will auto-generate that code for you. Think about a library already has written the code for you. You just invoke that and do everything. Okay, so you are programming at a higher level. So all of that is still there underneath. You just don't see it. Okay. Okay, so now let's look at semantics and then we'll think about a little more detail. So as far as the client is concerned, invoking a remote procedure from a semantics perspective is same as invoking a local procedure. When you make a remote procedure call, you are going to wait for a response. Just as when you make a local procedure call, you wait until that procedure is executed and returned a value. Okay, essentially, the execution goes to the function, and then when it returns, then you continue executing this function. Okay, same is true in case of remote procedure call, except that you're now waiting for a network message to return to you before you can continue execution. So there's message communication involved. So you make your RPC request, the server executes that request, sends back a reply, and then the client method is going to return with some value. If it's add, you'll essentially get the result of the add. Okay, so until then you're blocked. So essentially RPCs are blocking by default. They're also called synchronous. Okay, we'll see other ways to do non-blocking RPCs next time, but as of now, the semantics are same as making a local procedure call. Okay, that's first thing. Okay, there are several other details you want to think about as well. Okay, so when you and it's instructive to understand how local procedures differ from remote procedure. Okay, when you make a local procedure call, your program has a stack. Okay, you are going to push all the arguments on the stack and call a local procedure. The local procedure is going to look for all those arguments on the stack. That's what is shown here. Okay, so you essentially have also variables, return address, and all of this kind of stuff. Okay, when you make a remote procedure call, okay, there is no such stack because the code is somewhere else. You have to send all of this information over a packet and send it over to the server. Okay? And that has certain implications. Okay? First implication is you cannot pass pointers anymore. Okay? So if you know C or C++, you heard of pointers. Right? A pointer is essentially a memory address. Okay? You can, to a local procedure, you can pass a pointer. When it dereferences the pointer, it goes to the memory address and looks up whatever is there, pointed to by the pointer. Okay? When you send something over a network, this pointer is meaningless because the pointer is a memory address on the source machine. If you say pointer 100 and then you dereference it on the server, you are looking at location on server's memory address, which makes no sense, right? Because the pointer is pointing to a buffer on the client side. Okay? So essentially, you cannot pass arguments that involve pointers. Okay, that's the first problem. Okay, second, which is an equivalent problem, is when you pass arguments, you have to pass them by value. You cannot pass them by reference. Okay? When you pass arguments by reference to any function, you are essentially passing pointers. And when you dereference it, you are going to get whatever that thing was referring to. Okay? Now, since you are essentially traversing over a network, you can't dereference over a network because dereferencing requires you to point to memory locations on whoever called the function. Okay? So all argument passing has to be by reference. You cannot, by value. You cannot pass arguments by reference when you RPC. This is a limitation. Yeah, I said everything looks like it's a local procedure call, not quite. In a local procedure call, you can pass arguments by reference, you can pass pointers. You cannot do that in a remote procedure call. That will give you an error. It will actually, your code will not compile because the compiler will throw an error. Okay. So these are all restrictions, and the restrictions make sense because we don't have a way yet to dereference things over a network. Later on, we'll see ways to do that as well. But by default, we assume that doesn't exist. Okay, yes, question.
We have to keep in mind that don't pass it as an argument, or does the RPC underneath would transfers the reference of, for example, this into a pass by value?
Right. So the question is, can you, what does not passing by reference mean? When you make an RPC call, you have to assume that all the arguments are passed by value. You cannot actually have an argument that's passed by reference, which you could have in a local procedure call. That's what it means. Okay? The reason is that if you look at what is shown in that picture, okay, all the arguments has to be copied over and sent over a network. So you cannot pass references because here memory address I on this machine is not meaningful on this machine. Right? So you have to pass everything by reference, by value, not by reference. Okay. You cannot also have global variables in a RPC program because global variables sit in a memory address of the client. Okay, you cannot access a global variable from a server. Right? So you cannot have global variables across processes. You can have global variables within a process, but the server program cannot call a global variable that sits in a or cannot access a global variable that sits in the client address space. Okay? That is also not meaningful. Okay? So these are all restrictions. Okay? I'm going to talk about what marshalling means in just a moment, but it is important to keep in mind some of the restrictions of RPCs. Okay, so essentially you have the client program, you have the server program, you have remote procedures, your RPC compiler generates this extra code, which is called stub code. You link it together, and then you have a client and a server that can communicate. The server code will have all the socket code, all of the code to send messages and all of that for you. Okay, so, and I'll show you all the steps that RPC call invokes. Okay, those steps are actually shown already in that picture I showed you. Okay, so you call the procedure in the normal way. When the program figures out this is a remote procedure, it's going to go to the stub code. Okay, the stub is going to build a message saying here is a new function invocation. It's a remote procedure. Okay, you send that to the OS. The OS is essentially going to send that to the server. What is not mentioned here is that you actually have to establish a TCP/IP connection between the client and the server. Okay? So of course, you can't just send a message to the other machine before doing that. But as part of sending the message, you'll establish a socket connection. Okay? The remote OS is going to receive the message, hand it to the local stub. The local stub says, okay, what is this message for? It's for the add function. It's going to call the function, execute it, send back a response. Okay? So this is how things are going to work. Now, there are several details we have glossed over that actually become important when you think about implementing remote procedure calls. Okay, the first one is, what assumptions do we make about the client and the server? Okay. Should they be running the same OS? Can they run different OSs? Can a Linux machine call a remote procedure running on a Windows machine? Can an x86 machine call an RPC that is running on an ARM machine? Okay. Now, these things are important because we made certain assumptions, okay, which you never have to worry about if you have local, you make local function calls. Okay. One assumption is architectural assumption. Okay. So you might have two kinds of architectures. One is called Little Endian, the other is called Big Endian. In Little Endian, the leftmost bit is most significant and is the opposite in the other. Okay. So I send an integer. Okay. Suppose it goes from a Little Endian machine to a Big Endian machine. Okay. If it interprets it the wrong way, the argument is incorrect. Right? Because I just sent an integer, it's a 32 or a 64-bit string. I mean, not a bit string, but it's a set of bits. Right? So which way you interpret it will change the value of that integer. Okay. So if you assume everything is homogeneous, this problem doesn't occur. Right? Because you say I can only have Linux x86 machines talk to another Linux x86 machine. But that's going to limit how you write your distributed application. Okay, if somebody wrote a server that runs on Windows, does that mean Linux client cannot access it? You don't want that limitation. You want cross-platform access for RPCs. Okay? So to do this, you have to essentially send your arguments in a way where you can essentially deal with these cross-platform differences. Okay? You might also have 64-bit machines and 32-bit machines. Okay, I send the integers as 32 bits, but on the other end, maybe all integers 64-bit. You want to deal with all of these underlying details. Okay? And so the way we are essentially going to do this is a special technique where we are going to package all of the arguments, okay, in a way that any machine, regardless of architecture or operating system, can interpret it the right way. Okay? And this is called marshalling and demarshalling of arguments. So marshalling of argument says, I'm going to take anything you want to send, whether it's an integer or a complicated data structure, 3-dimensional array, whatever it is, I'm going to essentially package it in a way that any other machine, regardless of the OS, regardless of its hardware architecture, can interpret and reconstruct exactly the way the client said it. Okay? So this is called marshalling, and marshalling is packaging, and unmarshalling means unpacking. Okay? And the way we are going to do it, this is not really very hard. The way we are going to do it, we are going to define what's called an external data representation, or XDR. Okay? This says, regardless of your native architecture, your native operating system, when you send a message, this is the format you have to send it in. Okay? So we can say, for example, all integers in XDR format have to be little endian. Okay? So we define this. So if you're a big endian, then you have to flip the bits before you send it. Okay? If you are the same architecture, you do nothing. But you are agreed that all parties agree that this is XDR. This is how bits are going to be sent. This is how you have to define integers. So when something comes, you know how to interpret it. You don't have to worry about, is the client a different architecture or something like that. Okay? So you always translate your arguments into an XDR format, which is predefined for that RPC system. So whatever comes back, you then translate from the XDR format back to your native format. Okay? So there's no confusion as to what is going on. There's always a proper interpretation of what has come to you. Okay? Now, there are also other details of how do you take a 2-dimensional array and how do you send it as the byte stream and reconstruct it. Okay? In Java, you can send entire objects. Okay? Objects will have code, it will have state. How do you actually reconstruct it? All of that is also defined by the marshalling of arguments in the XDR format. It will say, if you want to send a 2-dimensional array, should you send them in row order or column order? Because you have to decide that when you reconstruct it. Okay? So that is all defined. So it's always, you always do whatever that format says. So it's going in a proper way. And then you can always reconstruct it exactly the way it was sent. Okay? So not just sending integers and what are the architectural differences, but also more complex data structures. How do you send it? Okay? Now in the Java world, okay, marshalling and demarshalling is done using what is called serialization. Okay, so Java has something called serialize and deserialize objects, which is also used incidentally to store an object on disk and reconstruct it at a later time. Because the exact same concept is also used for network communication, for things like RPCs in the Java world, that's called RMI. Okay? That's essentially what we are going to do for marshalling and demarshalling in Java. Is that clear? Any questions here? Yes. But question is this standard representation norm for all networks, or is this established between just the sender and the receiver? Right? So it is essentially a norm at a language or the RPC library level. So if you are using a certain RPC system, it is decided that that is what you are going to use. Okay? We are not allowing one RPC system to talk to another RPC system. We're saying at least the libraries that are using RPCs have to be the same, but the OS and all the other details can be different. So if you're using Java, Java has decided what it is. So any Java program on one machine, JVM can talk to another JVM using the same method. Okay? So that's what we mean here. Any other questions? Yes.
How we pass pointers, it says that if a points without defined data structure pass a point, and the server side passes a point. What is the symbol for that?
Yeah. So question is, how can you pass pointers? Because we said you cannot actually pass pointers, right? So the only way you can actually pass pointers is to take the object that the pointer is pointing to on the client, send that entire object over, okay, and then make a local pointer there and send a pointer to that. Okay, that's one way to do it. You don't have. You can just say, I prohibit pointers. So if you write a code with pointer, compiler gives an error. Okay, but you can write another RPC system saying, I'm not going to prohibit it, but I'm going to dereference the pointer, take the object it's pointing to, send that entire object, okay, and then keep the copy of that object there and make a local pointer and pass that pointer. So it will look like when you dereference, you're still looking at the same memory region that you had on the client. That's an alternative. You don't have to do that when you write an RPC system, but some RPC system will exactly do that. Okay. Repeat your question again. What is your? Yes. Yes. So question is about global variables, and I said you cannot actually use global variables when you're doing RPCs. Okay? So essentially any code that is a remote procedure, invocation or the code should not use global variables. Okay? But if you have other local functions in your program which have nothing to do with those remote procedures, those can of course use global variables like you're writing a normal program. That's all it needs. Right? So if you have local functions that are just really local code, they can do whatever you write in a centralized program. Only when you have remote code, you don't have to do that, or you should not do that. Okay. So now we get to the question of how does the client locate the server? Somebody had asked this question before. So there are multiple ways to deal with it. Okay, the simplest way is, at least if you know where the server is running, okay, if you know the IP address, you at least specify the IP address on the client side. And then the RPC code is going to take care of setting up a socket connection as the simplest method. Okay? And that is what I had showed you in the socket code, where you put the IP address. Same thing will happen on the client, except that the code is auto-generated. That's one way. Okay? The second way to do this is that any server that provides an RPC service will register with the naming or a directory service. It will say my program name is foo. I provide this kind of service. I provide a print service, HTTP service, whatever it is. Okay, so there's a directory of all the services that are running over a network. Okay. So the client, before it establishes a connection with the server, first looks up the naming service, saying, is there a service with this name running somewhere on my network? Okay. And then if the answer is yes, the directory service will say, yes, there is one. It's running on this machine. That's the IP address, that's the port number, and so on. And then the client can connect to it. Okay. Again, looking up the naming service, all of that is going to be done by the stub code. You still don't write that code. But that's an alternative approach for how you can locate where the server is. Okay. So there are two ways. When you write the client, know where the server runs. So you write the name and give it to the program. Or you make your program look up a naming service, which assumes that the server has registered itself with the naming service. Okay, the naming service may say there is no such server running, in which case the client will not be able to communicate. Okay, so either of these two are okay. Okay, any questions on what I said? Because now we'll talk a little bit about implementation details. Okay, so first part of the implementation detail is to understand what happens if there are failures over a network. Okay? This you don't really need to worry about when you're writing local function. Okay? If you call a local function, if there's a failure, the entire process has crashed. Okay? The function is not going to return because the program itself has crashed. Okay? Now, when you're writing a distributed program, the client may send a message to the server. It's asked for the add. The message is gone. The server was processing it, and the server crashed. The client is waiting for a response. There's no response that's going to come because the server is actually gone. So part of your process is still running, which is your client code, but the server code has disappeared. Okay, how do you deal with this? Right, and you can have all kinds of other problems. The messages might get lost. Okay, you send the add message, never got to the server. Server is running, but the network lost your message. The server may have executed, but the reply got lost. Okay. So all of these cases can occur. So when you write your RPC system, you have to decide how you're going to deal with it. And you have to let the programmer know that such and such things can happen. These are exceptions that can occur, and this is what you should do if they occur. Okay. So here are the types of failures. First one is client cannot locate the server. Server is not running. Okay, you can't do anything. You have to basically make sure somebody restarts the server. Okay. So there's nothing you can do there. The second one is your request message. Okay, the RPC request message got lost. It never got to the server. So in this case, you can have a timeout. You can say, if I don't hear back within time T, I'm going to retransmit. Okay, your stub code will do this. You don't have to do this. Okay. So you can essentially retransmit the request saying you will send the add message again, and then you'll get back a response. Okay, that's one way to do it. Okay. The replies might get lost as well. Okay. Maybe the add message executed, a response was generated, and when the response was traversing the network, it got lost. Okay. The client is still going to time out because it didn't hear back from the server. It is going to resend the message. Okay. The add will execute again, and a response, this time a response may come back. And that's okay. Okay. With one detail. Okay. If the RPC message is changing any state at the server, if you send the same message twice, you may actually have an incorrect result. Okay. What does state mean? So you could say this is a bank server. Okay. I could say add $100 to this account. That's my RPC message. Okay. I sent the message executed, and a response got lost. Okay, saying the account was updated. Okay. You again send a message saying add $100 to this account. Okay. You will execute it again. Response comes back. Okay. But now clearly the result is incorrect because you intended to only increment the account balance once, but incremented it twice. Okay. So in this case, the reason is you have some state that you're modifying at the server. Making the same operation twice will change the state twice, and you may get an incorrect result. You only intended to do this because you thought the RPC never executed to begin with, because you never heard back. So you timed out and you sent back the request again. Okay. So you want to avoid these problems. One way to avoid the problem is to say that request execution is idempotent. Okay. Idempotency is a property that says no matter how many times you send this request, okay, it's only going to have the same result. Okay. So you want to make sure that even if you increment this account balance by $100 10 times, it's not actually going to give you 10 times the amount in the balance. Okay. So you have to write your RPC system to deal with this. Okay. And the way you are going to have to do it is in the implementation, you will have to see, has this request already been processed? If so, you don't actually execute it again. You cache the result of the previous execution and you just send back the response again. Okay. That's one way by which you deal with idempotence. You keep a request cache, a response cache rather, at the server. So if the same request comes, okay, you will actually just send back the response on the cache instead of executing that method again. Okay. Okay. This now requires that every RPC message has a unique ID. Okay. Because how do you know if you get a message saying add $100 and then you get another message saying add $100 to that same account? Do you know that this is the same message that came twice, or you actually intended to send it twice? You need to be able to distinguish between the two cases. So what you will do is every RPC request is going to go with a unique ID saying this is request number, and you put an ID in there. Okay, so you can now track what requests have been received, which have been executed, and so on. So if you're going to retransmit an RPC request, you better use the same ID that was used previously. So the server knows this is a retransmission. It doesn't execute it again. Otherwise, you cannot guarantee idempotency. Okay? So that's what it says. Use sequence numbers. You add sequence numbers to your RPC message so the server can track what is going on. Okay? Then you can deal with errors. Okay, if you haven't executed this, you execute it. Okay, if you have, then you just take the response from the previous execution, which you cached, and send back that response. Okay, this is called idempotent execution, but that's dealt for lost replies. Okay, and then you can have server failures where the server crashes, okay, and maybe it reboots. And you are sending the same request multiple times because you timed out and you kept sending. Eventually it restarts and then your request executes. Okay? Now the question is, if you get back a response, what does it tell you about your RPC request? What does the server guarantee? Okay? What it should guarantee is no matter how many times you sent that request, okay, you want exactly one semantics, which means that the server executed it exactly once. That guarantees your idempotence. Right? So it says no matter how many times you transmit, I give you, if you get back a reply, you are guaranteed that it doesn't matter how many times you ask the server to execute this operation, it has executed it exactly once. That's what you want. Okay? But that's hard to achieve because you have to deal with all kinds of failures. Okay? The simplest semantics is at least one semantics. At least once means if you got back a response, the server executed it at least once. If you retransmitted it, may have executed multiple times. Okay? This system does not guarantee idempotency because your same request could have executed more than once because it says it executed at least once. It could have executed k times if you send it k times. Okay, just that the replies were getting lost, so you kept resending. Okay? So in this case, the system is not going to guarantee idempotency. You have to deal with this at an application level. As a programmer, you have to write code to make sure this is not going to cause bad results. The system is saying it will keep sending whenever request comes. It's not going to guarantee an idempotency. Okay? So you will have systems that do this. In fact, the simplest RPC systems don't do any idempotency. They leave it to the programmer. You deal with it. System not going to give you any properties like this. Okay? But you can write systems that will actually do this for the programmer if they do exactly what's. Okay? And then you can have at most ones, which says you get at least executed at most once, or you can have no guarantee at all. This doesn't tell you anything. Okay, so this is all properties that an RPC system designer has to think. What is it that you want to give to your programmers? Okay? The more you give, the better it is for the programmer, but the more complex your RPC system. Especially if you want exactly one semantics, you want to ensure everything is idempotent, your stub code, your RPC compiler, all of that has to write more code for you automatically to deal with all these things. Okay? So when you write RPC code, you got to understand what is the system giving you. And anything it doesn't give you, you have to write as a programmer. The more it gives you, the easier it is for you to write a program because you don't have to deal with failure properties. Okay? Now, many of these things that I mentioned here will not occur if you use RPC systems that run over TCP/IP. Because TCP/IP takes care of network packet losses for you. Okay? You are not going to get a case where you lost the request or you lost the reply, because if the TCP/IP code will actually detect that and retransmit for you. Okay? However, if you run your system on something called UDP, which is a sister protocol to TCP/IP, it does not do any retransmission. It does not detect lost packets. Okay? It doesn't do all of that for you. Then at the application layer, which means at the stub code, you have to deal with all this. Okay? So some things become simpler if you just use the right network protocol stack. You don't even have to write code in the RPC system. The network takes care of it. Okay? But the network is not going to take care of client failures or server failures. That you still have to deal with. But at least message losses over the network, it will retransmit. So you don't have to keep retransmitting or deal with all of these issues. Okay. Any questions here? All right. So there are also all kinds of things that will happen at the client. So what happens if the client fails, but this is a long running function that the server is still performing. So you call some RPC method, maybe it takes 1 hour to compute because it calls some database query or something like that. Okay? But the server so not the server, the client crashes. Should the server keep computing or should it terminate? Again, the answer to that depends on what kinds of abstractions or guarantees you want to give. So if the server is performing an RPC computation, but the client crashes, this is called an orphan RPC because the entity that made the call is gone. Okay, it's no longer running or executing. Okay. So what do you do with orphan RPC? Okay, one is called extermination, where you essentially keep a log at the client. OS keeps a log saying if the process crashes, the OS sends a message saying terminate this because the client process disappeared. Okay, so the OS is dealing with this for you. That is called extermination. Okay. Reincarnation says you divide time into what are called epochs. At the end of each epoch, you say which here are the RPC calls that are still executing. Are all of these clients still functioning on the network? If not, at that point, you will just go and terminate, clean up all of the orphan RPCs that were created in the previous time period, previous epoch. Okay. This is essentially reincarnation and general reincarnation, which says general reincarnation says that if the client is no longer there, try to find if it has restarted somewhere else. Is it now listening on a different IP or a different port number? If you find it, then you can actually send back a response. Okay, you delete it only if you cannot find it. So you try to locate the client if it has restarted. Okay? And then expiration is the simplest policy. It says that whenever an RPC computation starts, you will start a timer. Okay? Say I give 5 seconds. Okay? At the end of 5 seconds, if the RPC is still running, you pause it, you send a message to the client saying RPC is still executing. Do you still want a response? If a response comes back saying yes, you know the client is up because it sent you a response saying yes, you continue for another, extend the expiration time and continue and so on. So here, every so often, you're explicitly checking that the client is still functioning and so on. Okay, and only then do you continue. If not, you terminate. Okay, simple policy. Okay. Now, all of this only makes sense if your RPCs take a long time. If you're going to write an RPC that takes 1 millisecond to execute, you don't need any of this. But there will be RPCs that may take hours to compute because we said it could be arbitrary functions. You may write a function that does a long running computation. So in that case, you have to deal with all of these issues. Okay, yes, question. Okay. Is there a best practice as to which one to choose? So first of all, all of these are for the RPC designer. Programmer doesn't actually get a choice. If you say, I am going to use Java RMI, the JVM designer has made one of these choices for you, and you are going to go with that. Okay, this is saying if you are a distributed system designer who's writing an RPC system for application developers, these are ways you can write your system. Okay. Now, as to is there a best practice, you have to deal with failures in some way. So long as you say, this is what I have chosen in my RPC system, and you explicitly write that in your documentation, so application developers know what kinds of exceptions can occur and what they mean, that's good enough. And there is no right or wrong, because the more you do, the more complex things get. The less you do, the simpler it is, but then you're putting more burden on the programmer. Which one is the most common? Okay, so typically most RPC systems don't actually deal with client failures at all. But having said that, the few that do actually have looked at expiration as a simple way to do it. Okay? The simplest approach is don't deal with failures, let the programmer deal with it. Right? So you don't actually, but that's also the most complex for the programmers because you have to deal with it in your code. Okay? So let me just skip the implementation issues, do a quick mention of Sun RPCs, and then we'll stop here. So Sun RPC was the original system that developed RPCs for broad use. Okay? So there was a long time ago, maybe decades ago, there was a Unix operating system called Sun OS. And they were actually designing a network file system called NFS, which still exists today. Okay? So they decided the way clients and servers are going to communicate for a network file system is using RPCs. Okay? So designed RPCs. So when a client wants to write to a file, it calls the write RPC, and then you send a message to the server, it performs the write. When you want to read a file, you call a read RPC. Send it to the server reads the file and sends you back some data. Okay, that's how they designed the file system. Then they realized that this RPC system is more broadly applicable, and anyone can use this RPC concept to write a distributed application. So they made all the tools available. Okay, and now anybody who used that OS would also write their own RPC based program. Okay, so that's kind of a small history behind how RPC systems evolved. This was back in the 1980s. Okay, originally they ran over UDP. So you had all kinds of network failures, messages got lost, and so on. Then they switched to TCP, where things got better because TCP dealt with things as network losses and things like that for you. Okay, and then XDR essentially was defined initially as part of the Sun RPC system, still exists today, where they said it's all big Indian order for 32-bit integers. Whenever you send, you have to convert to big Indian and send. If you're little Indian, you have to swap everything. Okay, and then you can see it says you essentially retry once. If there's a timeout, you retry once, there's at least 0 semantics, which means that there's no idempotency given to you by default and so on. Okay. So these were all design decisions they made. Okay. It doesn't mean it's right or wrong, but that's what essentially was done in the RPC system. And I'm going to essentially since we ran out of time, we'll talk about this port mapping, and I'll show you a small snippet of code how to write RPC programs next time. Okay, so today let's stop here and then we'll continue on Monday.